Hello. Today we are moving on to studying a fundamental topic in modern logistics, warehouse management systems, known as WMS. Look at the screen. The visualization of a warehouse as a microchip here is not just for aesthetics. It reflects a key transformation in the industry, the transition from the chaos of institutional memory to absolute algorithmic precision. Imagine a classic non-automated warehouse. Its efficiency often relies on the experience of a single warehouse worker who has been working there for years and is the only one who knows the topology of specific goods. This institutional memory is a critical vulnerability. If such an employee goes on sick leave or resigns, processes become paralyzed. Scaling a business under such conditions is impossible. Modern WMS radically solves this problem. It is not just a spreadsheet for inventory accounting. It is a full-fledged digital brain of modern logistics, which takes away the information monopoly from personnel. Its task is to manage every action of employees and warehouse equipment in real time, relying exclusively on mathematical algorithms. Pay attention to this slide. On the left, we see a classic illustration of the problem of non-automated logistics, total dependence on the human factor. With a high degree of probability, in many enterprises, the storage topology still exists exclusively in the head of one experienced warehouse worker. He remembers that specific parts are in the third row behind the blue barrels. This phenomenon is called institutional memory in professional circles. But what happens when such an employee quits or goes on vacation? Knowledge of the product's location literally disappears with the staff. From an operational management perspective, this is a critical vulnerability. Such an approach makes rapid business scaling impossible. You cannot hire additional student staff during peak sales seasons and expect their efficiency. They will simply wander around the warehouse looking for the right box. On the right side of the diagram, the only way out of this situation is shown: the creation of a digital twin of the warehouse. The space is digitized, and each pallet position receives its unique address and physical characteristics. We take away the monopoly of knowledge from people and transfer it to an information system, protecting processes from personnel risks. Let's move on to the next slide, where we need to clearly distinguish between accounting and space management paradigms. Students often confuse corporate ERP systems and WMS, so let's clarify things. An accounting system, for example, an inventory management module in a hypothetical SAP, works exclusively with quantitative and monetary indicators. Its main goal is to record the historical fact of a transaction. It says, the company currently has 500 units of goods on its balance sheet. For a financial director or sales manager, this information is sufficient. But from the perspective of warehouse engineering, this figure is static and, frankly, dead. In contrast, WMS is an execution class system, meaning a system for continuous operation execution. Its basic dimension is not just in SKU, but a three-dimensional spatial coordinate, X, Y, and Z axis. It knows the exact location of every pallet or box in the warehouse. Let me give you a practical example. The ERP system shows the availability of 50 pallets of a popular product, and the sales department confidently confirms shipment to the client. But ERP does not see physical reality. WMS, however, knows that out of these 50 pallets, 10 are currently blocked on the 5th level due to scheduled maintenance of the high bay stacker. Another 5 are undergoing quality control in the quarantine zone, and only 35 are available for quick picking. That is why WMS does not just record balances ex post facto. Its focus is on real-time action. It algorithmically controls every movement of warehouse equipment and personnel, issuing atomic commands to data collection terminals. Where to drive, what to scan, and where to move. This is a shift from passive accounting to active orchestration of physical processes. Now let's look at the architecture of warehouse processes. Any WMS, regardless of the developer, builds its logic around 5 basic pillars of operational activity. Let's briefly go through this macrocycle. The first pillar is receiving. The key technology here is ASN, Advanced Shipping Notice Validation. A modern warehouse knows what is coming to it even before the physical arrival of the truck. WMS performs algorithmic reconciliation of actual barcodes with the expected document, blocking any mismatches already at the unloading stage. We don't look for errors later. We prevent them from happening at the input through hardware. The second stage is put away. Dynamic slotting mechanics are activated. The system itself analyzes the cargo's master data, weight, dimensions, and finds the single optimal location with the shortest travel distance, directing the forklift driver there. The third and most expensive process is picking. Here, WMS takes on complex mathematical routing. Instead of a person with a paper list running chaotically around the warehouse, the system generates optimal picking waves, or even integrates with a fleet of mobile robots, eliminating idle travel for personnel. The fourth pillar is packing. Today, this is already the territory of spatial computer vision and neural networks. The system can estimate the 3D dimensions of the picked goods and suggest the ideal box to minimize transporting air by mainline carriers. And the fifth process is inventory. Forget the Soviet approach of closing the warehouse for 3 days for revision. WMS implements a continuous background audit algorithm, cycle counting. The system selectively generates tasks to check specific cells during normal operation. The main point: WMS is an end-to-end management of these business processes in real time. The completion of one transaction instantly triggers the start of the next. Now we will look at inbound logistics processes. Let's start with receiving. The classic problem of an unautomated warehouse is blind trust in paper invoices. WMS works differently. The process is based on the integration of ASN, Advanced Shipping Notice. When an operator scans a barcode at the ramp, WMS implements a control check algorithm. The system automatically validates the actual quantity and SKUs against your purchase order, PO data. If a mismatch or shortage is detected, as shown in the interface on the left, the system immediately blocks the transaction and generates a discrepancy report. This allows a substantiated claim to be made to the supplier before the vehicle leaves the dock. But the most interesting part happens at the put-away stage. Pay attention to the visualization on the right. Here, WMS performs the function of a safety engineer, operating with algorithms of topological constraints. The system matches the cargo's master data with the physical characteristics of the cells. The screen shows a typical situation. A stacker driver tries to place a pallet weighing 1,200 kilograms on the 5th level of the rack. However, the beam of this level is designed for a maximum of 1,000 kilograms. In manual mode, this would lead to a collapse of the structure. But WMS knows these limitations. The terminal issues an error and blocks the transaction. The system simply will not accept scanning the barcode of this cell, hardware preventing an accident and redirecting the driver to a safe location. Thus, WMS eliminates the human factor both in document accounting and in matters of physical warehouse safety. Let's move on to the order picking process. Historically, this is the most expensive stage of warehouse logistics, as it requires the largest investment of human labor. On the left side of the slide, the classic model called person-to-goods is illustrated. In this paradigm, the system or foreman assigns a task to the employee, and the picker physically moves through the warehouse from cell to cell. Note the statistics. The basic productivity here is only 80 to 100 lines per hour. At the same time, the idle travel of personnel can reach 15 to 25 kilometers per shift. This results in tremendous physical fatigue and inefficient use of working time. On the right, we see the modern standard of automation, the goods-to-person model. Here, WMS acts not just as a route planner, but as a system for orchestrating mixed fleets. Through an API, it transmits coordinates not to a person, but to autonomous mobile robots, AMR. The robot drives under the target rack, lifts it, and brings it to the active picking zone directly to the employee's hands. Thanks to this, idle travel for personnel is eliminated. Picking speed increases phenomenally, up to 400 to 500 lines per hour. For less automated zones, WMS uses a hybrid approach. The algorithm allocates a follow-me AMR robot, which follows the picker like a smart cart, and after loading, independently transports a pool of orders to the transit zone, allowing the employee to focus on picking. Let's move on to the packing and shipping stage. Traditionally, this process requires the operator to manually scan the barcode of each item before placing it in a box. Today, however, we are seeing the implementation of spatial computer vision systems. Pay attention to the left side of the slide. Arrays of video analytics cameras are deployed above the workbench. When an employee picks up an item, the neural network recognizes its physical contours and instantly validates its compliance with the digital twin of the order. This eliminates mismatches at the final stage without unnecessary scanner manipulations. But the main financial value of this stage lies in the work of the cartonization module, dimensional weight tariffication. Almost all mainline carriers tariff shipments by dimensional weight. Paying for transporting air means burning business margins. To avoid this, WMS analyzes the 3D dimensions of the picked goods and predictively indicates to the packer the SKU of the ideal cardboard box. As soon as the box is closed, the system uses an API to connect to the carrier's server, instantly prints a ready-made shipping label with tracking, and routes the cargo to the correct dock door for loading. The next slide reveals the basic prerequisite for any automated system, the digitalization of space, or the development of topology. For algorithms to manage logistics, the physical world must be transformed into a digital map. The system does not operate with abstract concepts like, put this in the corner by the window. For WMS, a warehouse is a rigid three-dimensional coordinate system, where each cubic meter has its own unique address and barcode. Pay attention to the screen. Standard addressing logic is built on a hierarchical principle. Zone row section level cell. As an example, we have the address A05-12-3-1. But I want to emphasize the most important thing. For the information base, this address is not just a navigation sign, it is a set of strict physical limitations. Each address encodes data about its capacity, height, width, and depth. Imagine a situation. A non-standard pallet arrives 1.8 meters high. Even if the warehouse worker visually sees an empty space on the rack and tries to scan this cargo there, the system will block the action if the height of that cell in the topology is only 1.6 meters. WMS hardware prevents human errors, preventing the cargo from colliding with the beams of the upper level, even before the forklift driver starts lifting the forks. Next, we approach the issue that directly affects the cost of maintaining warehouse space. This is the choice between static and dynamic storage. On the left, you see the traditional static model. It involves rigidly assigning rows to specific nomenclature, for example, televisions and air conditioners. The main disadvantage of this approach is that if a batch of televisions is sold out, these racks will stand empty. The warehouse worker has no right to put other goods there. Otherwise, he simply won't find them. Due to this artificial rigidity, the volume utilization factor rarely exceeds 60 to 65%. On the right is algorithmic dynamics, or managed chaos. With WMS, the system allows a pallet to be placed in any nearest available spot that fits its dimensions. The next identical pallet might be at a completely different end of the warehouse. The efficiency of space utilization in this case skyrockets to 90 to 95%. Consider a classic case of a distributor with distinct seasonality. Imagine a warehouse where the winter tire zone is empty in summer. If the company urgently buys a large batch of air conditioners at a favorable price, static logic would refuse to accept them because the designated zone for air conditioners is already full. In contrast, dynamic WMS erases these boundaries. It treats the warehouse as a single pool of volumes and algorithmically fills any free coordinates with new cargo. This allows the enterprise to absorb anomalous deliveries without needing to rent additional space from 3PL operators. Now we will analyze how the system chooses a place for cargo in dynamic storage conditions. Dynamics is not a chaotic scattering of goods throughout the warehouse. It is governed by strict mathematical algorithms that form the slotting process. The main goal of slotting is to minimize the travel distance of equipment and reduce the physical fatigue of pickers. To achieve this goal, WMS analyzes historical sales depth and segments all nomenclature using the classic ABC analysis method. Pay attention to the golden zone, highlighted in orange on the diagram. This is the most ergonomic space on the rack, located at the waist and chest level of the employee. The algorithm rigidly reserves these cells exclusively for Group A goods, items with the highest frequency of access, fast movers. Placing the most demanded goods here eliminates the need to bend down or reach up. This saves seconds on each transaction and preserves the health of personnel. In addition, Group A is always placed closest to the dispatch zone. In contrast, Group C goods, slow movers, which are needed only episodically, are algorithmically pushed into the cold zone. These are the highest levels, 5th or 6th, or the most remote dead-end aisles of the warehouse. WMS will never allow a premium cell to be occupied by low-turnover goods. Intermediate transit blocks, accordingly, are filled with medium-demand goods from Group B. Let's move on to the next slide. We have just discussed classic ABC analysis. However, in modern international logistics, this is no longer sufficient, as such an approach is retrospective, it looks at the past. Today, predictive slotting based on artificial intelligence engines is becoming the industry standard. Pay attention to the visualization. Machine learning analyzes not only historical sales but also multivariate external triggers, promotion matrices, social trends, or, as shown on the slide, weather conditions. A neural network can predict a sudden surge in demand several days before the event. For example, a sharp cold spell is predicted. The system does not wait for orders to arrive. It proactively generates tasks for night warehouse defragmentation at 3 o'clock. Forklifts move pallets with heaters from the remote cold zone directly to the golden zone. What is the result? When the actual sales peak occurs in the morning, the goods are already on the shortest picking trajectory. We avoid transit congestion and ensure uninterrupted shipments. This is algorithmic demand anticipation. Let's move on to the slide where we will examine inventory management strategies. Having an address system and accurate balances is only half of WMS functionality. The main task of the algorithm is to determine which specific physical unit of goods needs to be shipped at a given moment. At this stage, the information system faces physical limitations or the dictates of the equipment. Two basic algorithms are presented on the slide. The first is FIFO, first in, first out. According to this, the batch of goods that arrived first must leave the warehouse first. This strategy is used for goods with an expiration date or a risk of obsolescence, e.g. home appliances. From an engineering perspective, the FIFO algorithm is ideally implemented through gravity roller racks, flow racks. A pallet is loaded from one side of the channel and rolls under its own weight to the unloading zone, ensuring that the oldest pallet is always first in line for picking. The second algorithm works with reverse logic LIFO, last in, first out. The priority for shipment goes to the goods that arrived last. At first glance, this seems illogical for logistics, But such a strategy is the only possible one for block storage areas of building materials or deep racks such as drive-in. In such structures, the forklift places pallets one by one deep into the tunnel. WMS understands that an attempt to retrieve the oldest goods from the bottom of the array will inevitably lead to a collapse of the structure or unnecessary rehandling of the cargo, so it forcibly directs the driver to take the outermost pallet. Thus, the inventory processing strategy in WMS is always strictly determined by the design of the existing racks. System algorithms must synchronize with the physical laws of the warehouse. If in the previous stage we talked about strategies dictated by the physical limitations of racks, here the focus shifts entirely to the depth of the cargo's digital footprint. We are considering informational algorithms FIFO and FPFO, where the system is guided exclusively by product attributes. The first strategy is FIFO, first expired, first out. According to this logic, the product with the shortest remaining shelf life is shipped first. This is a fundamental standard for food retail, FMCG, pharmaceuticals, and the chemical industry. Look at the diagram on the left. One box arrived today, but its expiration date is in just 1 month. Another box arrived yesterday, but lives for another 2 days. During picking, WMS completely ignores the arrival date or the convenience of the cell. The system will forcibly direct the employee to the batch that ages faster, ensuring zero write-offs due to expiration. It should be noted that this strategy requires integration with the GS1-128 standard or RFID, so that the scanner can read the expiration date at the time of receiving. The second, organizationally more complex strategy is FPFO, first produced, first out. Here, the basic reference point is not the date of arrival at the distribution center, but the date of manufacture at the factory. The need for this algorithm arises due to disruptions in global supply chains. Imagine a situation. A batch produced in January got stuck at customs, while the February batch passed without delays and arrived at the warehouse first. Under normal accounting rules, the system would ship the February batch first. However, the FPFO algorithm restores the correct circulation. WMS analyzes the production barcode and identifies the January batch as a priority. The main conclusion of this slide. WMS algorithmically ignores the convenience of product location for the sake of adhering to the priority of product freshness or production chronology. We've talked a lot about algorithms, but how exactly does a human interact with this system at a physical level? Here, it's worth paying attention to the evolution of machine-to-human interfaces. Today, paper lists, industrial tablets, and even voice terminals are being replaced by augmented reality, AR technology, or the concept of vision picking. On the slide, you see the workspace through the lens of a picker's smart glasses. WMS no longer forces the employee to read text coordinates from a display. The system transmits tasks as three-dimensional graphic polygons overlaid directly on the real racks. The glasses draw a navigation path directly on the floor and highlight the single correct cell with the contrasting outline. Moreover, the built-in camera automatically reads the barcode without pressing any buttons. From an operational perspective, this offers 3 fundamental advantages. First, the employee has completely free hands, which is critical when working with heavy containers. Second, the time for cognitive location recognition is radically reduced. Following a visual marker is much faster than searching for a section number. Third, and most importantly, strict hardware error blocking occurs. If an operator tries to pick cargo from another cell, violating the programmed strategy, e.g. FIFO, the interface will instantly block the transaction. The system makes process violations physically impossible. Let's move to the final slide of our lecture. Here we summarize not only the logistical, but also the informational transformations of warehouse systems. Pay attention to the evolution of IT architecture. On the left is the traditional monolithic approach, local servers or on-premise. Previously, WMS was installed on physical equipment directly in the warehouse. This created problems with updates and severely limited system performance. Today, the industry standard has become migration to cloud-based SaaS platforms built on a microservice architecture, as illustrated on the right. Instead of one massive block, the system consists of independent distributed modules, databases, analytics, API gateways. Why is this critical for operational logistics? Distributed computing allows seamless and elastic scaling of system capacities. When Black Friday or an unpredictable seasonal peak in transactions occurs, the cloud automatically allocates additional resources, preventing WMS paralysis. In addition, microservices ensure zero downtime deployment, the ability to update algorithms without a global warehouse shutdown. Integration with other corporate systems such as ERP or TMS now occurs via reliable message brokers such as Apache Kafka and Open REST APIs. In summary, modern automation transforms the warehouse from a passive storage facility into a transparent, managed conveyor. WMS guarantees 100% control over every transaction and ensures business resilience to any loads.